Hello there and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Maybe the day has been long and heavy, or perhaps you're someone who finds comfort in the gentle mysteries that surround us. Either way, you've come to the right place. Tonight, we're embarking on a quiet journey through the cosmos, not to be dazzled or overwhelmed, but to find peace in the vast and beautiful truths that drift silently through space and time. There's nothing you need to do now except rest. Let your shoulders drop, your breathing deepen, and your thoughts settle like cosmic dust, finding its place among the stars. We'll move gently from one soothing fact to another, discovering the calm rhythms of the universe, the patient processes that unfold over millions of years, and the quiet wonders that happen in the spaces between everything we can see. If these peaceful explorations help you unwind or give you a tranquil way to end your day, consider liking and subscribing to the channel. Now, let yourself get comfortable. Close your eyes if you'd like, and let's begin this slow drift through the most calming truths about our universe. Space has its own gentle weather patterns that flow like invisible rivers. Far from the violence we might imagine, much of the cosmos moves with the slow grace of weather systems. Solar winds flow outward from stars in steady streams, carrying charged particles across vast distances at speeds that seem fast, but are actually quite measured on cosmic scales. These stellar breezes interact with magnetic fields, creating boundaries and currents that shift and flow like atmospheric pressure systems on Earth. Between galaxies, there are cosmic winds that blow for millions of years, stirring gas clouds and shaping the distribution of matter with patient persistence. Even the most energetic processes in space often unfold with a rhythm that's almost meditative, like watching clouds form and dissolve in an endless sky. The universe hums with frequencies too low for human ears to detect. Throughout space, there are vibrations and oscillations happening constantly, but they occur at wavelengths so long and frequencies so deep that they exist below our ability to hear them. Stars pulse with internal rhythms as pressure waves move through their layers. Galaxies ring like enormous bells when disturbed by gravitational interactions. Even the cosmic web itself may vibrate gently as dark matter filaments respond to the slow dance of expansion and gravity. These cosmic harmonies create a kind of universal background music, inaudible but ever-present, like the deepest notes of an organ played in a cathedral larger than imagination. Cosmic recycling happens on timescales that make mountains seem momentary. The universe operates on the most patient recycling program imaginable. Elements forged in the hearts of ancient stars are released when those stars die, drifting through space for millions of years before being gathered into new stellar nurseries. The iron that once flowed through the core of a star that died before our solar system formed might now be part of a planet orbiting a young star in a distant galaxy. Gas expelled from one generation of stars becomes the raw material for the next, in cycles so long and gentle that they make geological time seem rushed. Nothing is ever truly lost, only transformed and relocated across the vast recycling centers of space. There are regions in space where time moves differently, creating pockets of temporal calm. Near massive objects, time slows down relative to less dense regions of space. This means there are places in the universe where time flows more peacefully, where moments stretch longer and the rush of existence becomes a gentle drift. Around some stars, in certain gravitational fields, time moves with the relaxed pace of a lazy afternoon that never quite ends. These temporal oases exist throughout the cosmos, quiet zones where the universe takes its time, where even light seems to move with less urgency. Interstellar clouds drift for millions of years like slow-motion weather fronts. Between the stars, enormous clouds of gas and dust move through space with the unhurried pace of weather systems that last geological ages. These molecular clouds can be hundreds of light years across, drifting slowly through the galaxy like cosmic fog banks. They're cold and dark and peaceful, moving so gradually that their motion can only be detected over thousands of years of observation. Within these clouds, the processes of star formation begin not with violence, but with the gentlest gravitational whispers, as matter slowly, patiently gathers itself into denser regions that will eventually become new suns. The cosmic microwave background radiation bathes everything in ancient, gentle warmth. Throughout all of space, there's a faint glow left over from the universe's early days, when it was young and hot and glowing like the inside of a furnace. This light has been traveling for over 13 billion years, cooling and stretching as the universe expanded, until now it reaches us as the softest possible microwave radiation. It's everywhere, filling every cubic centimeter of space with the gentlest possible warmth, just a few degrees above absolute zero. This cosmic background radiation is like the universe's memory of warmth, a tender glow that connects every point in space to the cosmos's peaceful infancy. Gravitational waves ripple through space-time like the gentlest possible tremors. When massive objects accelerate through space, they create ripples in the fabric of space-time itself. These gravitational waves travel at the speed of light, but they're so subtle that they barely disturb anything as they pass. They stretch and compress space by amounts smaller than the width of a proton, creating the most delicate possible disturbances as they carry information about distant cosmic events. These waves pass through planets, stars, and galaxies without leaving a trace, like whispers in a language that only the most sensitive instruments can detect. The expansion of the universe happens so gradually that it's imperceptible on human timescales. Space itself is growing larger, carrying galaxies away from each other. But this expansion is so gentle and steady that it can only be noticed when looking at the most distant objects in the cosmos. On the scale of solar systems, galaxies, or even galaxy clusters, this expansion is negligible. It's only across the vastest distances that its effects become apparent, like watching the slow drift of continents, but stretched across billions of years and billions of light years. The universe grows larger with the patience of geological time, multiplied by cosmic scales. Dark matter moves through ordinary matter like a cosmic breeze that touches nothing. The mysterious substance that makes up most of the universe's mass flows through space, through planets, through stars, and through us without interacting in any detectable way. Billions of dark matter particles pass through every square centimeter of your body every second, but they leave no trace, create no sensation, cause no disturbance. They're like a gentle cosmic wind that blows through everything, connecting all matter through invisible currents while remaining completely unobtrusive. This dark matter wind has been flowing through space for billions of years, shaping the universe's structure while remaining forever elusive and peaceful. The light from distant galaxies has been traveling toward us since before Earth existed. When you look at images from powerful telescopes showing galaxies billions of light years away, you're seeing light that began its journey when the universe was young and our solar system hadn't yet formed. This ancient light has been traveling through space for longer than our planet has existed, crossing unimaginable distances at a steady, patient pace. Some of this light started its journey when the universe was still forming its first large-scale structures, and it's been moving toward us ever since, carrying information about cosmic conditions that existed long before anything familiar had come into being. Planetary orbits trace smooth ellipses through space with mathematical precision. The paths that planets follow around their stars are perfect geometric curves, ellipses drawn by the interplay of gravity and momentum. These orbits are so precise and predictable that they can be calculated thousands of years into the future with extraordinary accuracy. Each planet follows its path with the reliability of clockwork, sweeping through space in graceful arcs that repeat endlessly. The mathematics that govern these motions are elegant and simple, describing curves of such beauty that they seem almost designed for contemplation. Stellar nurseries are regions where new stars are born in processes that take millions of years to complete. In the cold, dense cores of molecular clouds, gravity slowly gathers material together. But this process unfolds with extraordinary patience. What begins as a slight increase in density gradually becomes a concentration of matter that will eventually ignite as a new star. But the transition from cloud to star can take 10 million years or more. These stellar nurseries are places of gentle transformation, where the universe takes its time to craft new sources of light and warmth through processes so gradual they make human timescales seem instantaneous. The cosmic web connects all matter in the universe through invisible filaments. On the largest scales, galaxies aren't scattered randomly through space, but are connected by vast threads of dark matter and gas that stretch across hundreds of millions of light years. This cosmic web forms a delicate network that looks remarkably like neural networks or the structure of soap bubbles, with galaxies clustered at the intersections of filaments and vast empty voids in between. The web grows and evolves slowly as the universe expands, but its basic structure has remained stable for billions of years, providing a gentle scaffolding that guides the formation and movement of all large-scale cosmic structures. Neutron stars spin with such perfect regularity that they serve as cosmic timepieces. Some of the most precise clocks in the universe are not mechanical devices, but the collapsed cores of dead stars. Neutron stars can rotate hundreds of times per second while maintaining timing accuracy that rivals atomic clocks. These stellar remnants emit beams of radiation that sweep across space like lighthouse beams, and the timing of these pulses is so regular that astronomers use them to study subtle effects in space-time and even to detect gravitational waves. The universe has created its own network of cosmic chronometers spinning peacefully in the darkness with clockwork precision. Comets follow long, slow orbits that can take thousands of years to complete. These icy wanderers spend most of their time in the cold outer reaches of solar systems, moving so slowly that their motion is barely perceptible. For centuries or millennia, they drift through the darkness, following elliptical paths that eventually bring them closer to their star, where solar heating creates the beautiful tails we sometimes see. But even this dramatic phase is brief compared to the long, quiet journey through the outer darkness, where comets move with the unhurried pace of cosmic meditation, taking their time to complete orbits that span human history. The process of cosmic evolution unfolds according to gentle, predictable patterns. Stars form, evolve, and die according to well-understood physical laws that operate with remarkable consistency throughout the universe. The life cycle of a star depends on its mass and follows patterns that can be predicted with great accuracy. Low-mass stars burn their fuel slowly and steadily for billions or even trillions of years. More massive stars burn brighter but for shorter periods, following their own predictable evolutionary paths. These stellar life cycles create a cosmic rhythm that has been playing out for billions of years, with each generation of stars contributing to the gradual enrichment and evolution of the cosmos. Supermassive black holes at the centers of galaxies maintain cosmic balance through patient gravitational shepherding. These enormous objects, millions or billions of times more massive than our Sun, don't consume everything around them as we might imagine. Instead, they regulate star formation in their host galaxies with remarkable gentleness, controlling the flow of gas and energy across vast regions of space. When material falls toward them, the process creates outflows that push gas away from the galactic center, preventing runaway star formation and maintaining equilibrium. This cosmic thermostat operates over millions of years, keeping galaxies stable and preventing them from burning through their fuel too quickly. The black holes act like wise gardeners, pruning and tending their galactic ecosystems with invisible hands. Magnetic fields thread through space like cosmic silk, creating invisible highways for charged particles. Throughout the universe, magnetic field lines stretch across enormous distances, forming delicate networks that guide the movement of plasma and cosmic rays. These fields are incredibly weak by terrestrial standards, but over cosmic distances, they become significant forces, channeling material along graceful curves and spirals. Solar magnetic fields create the beautiful loops and arcs visible in images of the Sun's corona. Galactic magnetic fields help shape the spiral arms of galaxies and influence how matter flows between stars. These invisible threads connect distant regions of space, creating a hidden architecture that organizes cosmic matter with the patience of a master weaver. The vacuum of space contains virtual particles that briefly flicker into existence before disappearing again. Even in the emptiest regions of the cosmos, quantum mechanics ensures that perfect stillness is impossible. Pairs of particles and antiparticles spontaneously appear and annihilate each other in time frames so brief they barely qualify as existence. This quantum foam creates a subtle background activity throughout all of space, like the gentlest possible stirring in an otherwise perfectly calm pond. These virtual particles don't disturb the peaceful nature of space, but instead add a layer of quantum quietude, a whispered reminder that even emptiness is alive with the most delicate possible activity. Binary star systems dance around each other in orbital ballets that can last for billions of years. When two stars are born close together, they become locked in gravitational embraces that create some of the most elegant motions in the universe. They orbit their common center of mass with clockwork precision, sometimes completing their dance in hours, sometimes in millennia, depending on their separation and masses. Some binary systems are so close that material flows between the stars in graceful streams, creating bridges of glowing gas that connect them like cosmic ribbons. Others maintain their distance, circling each other with the dignity of formal dancers who never quite touch, but remain forever paired. Galaxy clusters move through space like slow-motion cosmic flotillas, taking hundreds of millions of years to traverse their own diameters. These enormous collections of galaxies, containing hundreds or thousands of individual stellar systems, drift through the cosmic web with majestic patience. The galaxies within clusters orbit around their common center of gravity in paths so vast and slow that completing a single orbit can take longer than the entire history of complex life on Earth. Hot gas fills the spaces between cluster galaxies, glowing softly in X-ray wavelengths and creating a gentle medium through which the galaxies move like ships sailing through luminous fog. The cosmic distance ladder extends measurements across the universe through a series of overlapping techniques, each building gently upon the last. Astronomers determine distances to nearby stars using parallax, the slight apparent shift in position as Earth orbits the Sun. For more distant objects, they use the brightness of certain types of variable stars whose intrinsic luminosity is known. For the most distant galaxies, they rely on the redshift of light caused by cosmic expansion. Each method overlaps with the next, creating a chain of measurements that extends from our solar neighborhood to the edge of the observable universe. This careful calibration has been built up over decades of patient observation, creating a cosmic measuring stick of remarkable precision and elegance. Planetary systems form from rotating disks of gas and dust that gradually condense into worlds through processes governed by gentle gravitational sculpting. When a new star ignites, it's often surrounded by a flat disk of leftover material from its formation. Within this disk, tiny particles stick together through electrostatic forces, slowly building up into larger and larger aggregations. Over millions of years, these growing bodies sweep up more material, eventually becoming planets. The process is remarkably orderly, with planets forming at specific distances from their star where different materials can condense. Rocky worlds form closer in, where it's too hot for ice to exist, while gas giants gather the lighter elements farther out, where the cold allows them to accumulate massive atmospheres. Tidal forces create some of the most subtle and persistent influences in cosmic systems, slowly reshaping objects over vast periods of time. The differential pull of gravity across extended objects creates gentle but inexorable changes that accumulate over millions of years. Moons gradually spiral away from their planets as tidal forces transfer energy between rotation and orbital motion. Binary stars can be slowly torn apart or pushed together by these same forces. Even galaxies experience tidal effects when they pass near each other, with long streams of stars being pulled out into space to form delicate bridges and tails that can persist for billions of years. These tidal sculptures, graceful structures in the cosmos, testament to gravity's ability to create beauty through patient, persistent influence. The interstellar medium fills the space between stars with an incredibly tenuous but vast reservoir of gas and dust. This cosmic atmosphere is so thin that the best vacuum chambers on Earth are dense by comparison. Yet it extends across such enormous volumes that it contains significant amounts of matter. Within this medium, shock waves from stellar explosions propagate for thousands of years, creating expanding bubbles and shells that glow softly in various wavelengths of light. The medium also contains complex organic molecules, the chemical building blocks from which planetary systems and potentially life itself can form. This interstellar ocean provides the raw material for future generations of stars, while serving as a gentle medium through which energy and matter flow across galactic distances. Red giant stars spend their final phases of life in a state of gentle expansion that can last for millions of years. When stars like our Sun exhaust the hydrogen fuel in their cores, they begin burning helium and other heavier elements, causing their outer layers to expand and cool. These red giants can grow to enormous sizes, sometimes large enough to engulf the orbits of inner planets if they existed in our solar system. But this expansion happens so gradually that it's more like a slow, cosmic breathing than a violent explosion. The star's outer layers become so tenuous that they barely qualify as solid matter, creating a gossamer sphere of glowing gas that can persist for geological ages before finally being gently expelled into space to form a planetary nebula. The formation of heavy elements in stellar cores happens through nuclear processes so gradual they make geological time seem rapid. Inside the hearts of massive stars, lighter elements are slowly fused into heavier ones through a series of nuclear reactions that can take millions of years to complete. Carbon fuses into oxygen, oxygen into silicon, silicon into iron, each step requiring higher temperatures and pressures than the last. The star builds up these elements in concentric shells, like an onion made of different atomic species. Only in the final moments of the star's life do these elements get distributed into space. But their creation was a process of extraordinary patience, with each atomic nucleus crafted through nuclear alchemy that unfolded over cosmic timescales. The life cycle of galaxies unfolds through phases of formation, maturation, and eventual transformation that span the entire history of the universe. Young galaxies are often irregular and actively forming stars, with bright blue regions marking stellar nurseries and ongoing cosmic construction. As they age, galaxies tend to become more organized, developing spiral arms or elliptical shapes as their internal dynamics settle into stable patterns. The oldest galaxies have often exhausted much of their star-forming gas and appear red and quiet, populated mainly by long-lived, low-mass stars. This galactic aging process happens so slowly that we can only observe it by comparing galaxies at different distances and therefore different ages. using the fact that light from distant objects shows us how they appeared in the cosmic past. Brown dwarfs exist in a peaceful middle ground between stars and planets, too small to sustain nuclear fusion, but too large to be considered planetary objects. These cosmic in-betweens spend their entire existence slowly cooling down from the heat of their formation, glowing dimly in infrared wavelengths as they radiate away their internal energy. They're often called failed stars, but this characterization seems unfair to objects that have found their own quiet niche in the cosmos. Brown dwarfs can persist for trillions of years, far longer than any true star, slowly fading but never quite disappearing. They represent a kind of cosmic patience, objects that have accepted their limitations and settled into extremely long, gentle declines that will outlast most other astronomical phenomena. The rotation of galaxies follows patterns so regular, they seem choreographed by invisible conductors across cosmic time. Most spiral galaxies don't spin like solid wheels, but instead follow what astronomers call differential rotation, where stars closer to the center complete their orbits faster than those farther out. This creates the graceful spiral patterns we observe, with density waves moving through the stellar disk like slow ripples in a cosmic pond. These waves trigger star formation as they pass, lighting up the spiral arms with newborn stars that shine brightly but briefly before the wave moves on. The entire process unfolds with such mathematical precision that galaxies maintain their spiral structure for billions of years, despite the fact that individual stars drift in and out of the arms like dancers changing partners in an eternal waltz. Asteroid belts represent zones of cosmic peace, where planetary formation reached a gentle equilibrium rather than violent completion. In regions like the asteroid belt between Mars and Jupiter, countless small bodies orbit in relatively stable paths, never quite managing to coalesce into a single planet, but never dispersing entirely either. These rocky fragments follow their elliptical paths with quiet dignity, occasionally bumping into each other in slow-motion collisions that might take thousands of years to complete. The gravitational influence of nearby Jupiter keeps the belt stirred just enough to prevent the asteroids from settling into a single massive body, creating instead a ring of cosmic gravel that has persisted for billions of years in stable, predictable orbits. Stellar associations are loose groups of young stars that form together but are slowly drifting apart as they age, like cosmic families gradually dispersing. Unlike the tightly bound globular clusters that remain intact for billions of years, these associations are held together only weakly by gravity and the shared motion inherited from their birth cloud. Over tens of millions of years, the individual stars follow slightly different paths through the galaxy, slowly spreading out from their common origin until they become indistinguishable from the general stellar population. This gentle dispersal process means that stars that once shared the same stellar nursery eventually become scattered across hundreds of light years, each carrying with them the chemical signature of their common birthplace. The cosmic background radiation provides a fundamental temperature floor that prevents the universe from ever becoming completely cold. Even in the most isolated regions of space, far from any stars or galaxies, This ancient light maintains a minimum temperature of about 2.7 degrees above absolute zero. As the universe continues to expand, this background radiation will continue to cool, but it will never disappear entirely. Billions of years from now, when the last stars have burned out and the cosmos has grown dark and cold, this faint glow will still persist, providing the gentlest possible warmth to an otherwise frozen universe. It serves as a cosmic memory of the hot, dense state from which everything emerged. A reminder that the universe was once young and warm and full of potential. White dwarf stars represent the final, peaceful phase of stellar evolution for the majority of stars in the universe. After shedding their outer layers as planetary nebulae, these stellar cores settle into a state of gradual cooling that will continue for longer than the current age of the universe. White dwarfs are about the size of Earth, but contain roughly the mass of the Sun, making them incredibly dense. Yet they pose no threat to their surroundings. They simply sit in space, slowly radiating away their stored thermal energy over trillions of years. Some white dwarfs are accompanied by faint companions that orbit them in systems so stable they could persist until the universe itself grows cold and dark. The galactic halo extends far beyond the visible disk of spiral galaxies, creating vast spherical regions filled with ancient stars and globular clusters that orbit in stately, elongated paths. These halo stars follow orbits that can take them hundreds of thousands of light years from the galactic center, moving so slowly that a single orbit might last longer than the age of complex life on Earth. Many halo stars are among the oldest objects in the galaxy, having formed when the Milky Way was still assembling from smaller proto-galactic fragments. They serve as living fossils, preserving information about the conditions that existed when galaxies were young and the universe was still finding its current structure. Molecular clouds serve as cosmic cocoons, where new stars develop in environments protected from the harsh radiation and energetic processes of open space. Within these dark, cold regions, temperatures drop to just a few degrees above absolute zero, creating conditions where complex molecules can form and persist. The clouds shield their interiors from ultraviolet light that would otherwise break apart delicate chemical bonds, allowing organic compounds to accumulate over millions of years. When gravitational collapse finally begins within these clouds, it happens gradually and gently, with material slowly flowing inward along magnetic field lines, rather than falling catastrophically toward a central point. The orbital mechanics of planetary systems create natural rhythms and resonances that maintain stability across cosmic timescales. Many planetary systems exhibit orbital relationships, where planets complete their orbits in simple numerical ratios, such as one planet completing exactly 2 orbits for every 3 of its neighbor. These resonant relationships aren't coincidences, but represent stable configurations that systems naturally evolve toward over millions of years. The gravitational interactions that create these resonances also help maintain the long-term stability of planetary systems, preventing planets from wandering too far from their assigned orbital zones or colliding with their neighbors. Cosmic dust grains drift through space for millions of years, slowly growing larger as they accumulate material from the tenuous interstellar medium. These tiny particles, smaller than the width of a human hair, serve as the building blocks for future planets and stars. They provide surfaces where atoms can stick together and form more complex molecules, acting as cosmic chemistry laboratories where the raw materials for rocky worlds and organic compounds are assembled. The dust grains themselves are often formed in the atmospheres of dying stars, beginning their journey as stellar exhalations before embarking on million-year voyages through interstellar space. The process of galactic chemical evolution occurs through countless stellar generations, each contributing slightly to the gradual enrichment of the cosmos with heavier elements. The first stars contained almost no elements heavier than hydrogen and helium, but as they lived and died, they scattered newly formed carbon, oxygen, silicon, and iron into space. Subsequent generations of stars incorporated these elements, creating slightly more complex chemistry in their planetary systems and stellar atmospheres. This cosmic recycling program has been operating for over 13 billion years, slowly but steadily increasing the complexity and diversity of matter throughout the universe. Tidal heating in the moons of giant planets creates internal energy sources that can maintain liquid oceans beneath icy surfaces for billions of years. The gravitational pull of massive planets like Jupiter and Saturn creates friction within their moons as they orbit, generating heat through the constant flexing of rock and ice. This gentle but persistent energy source can keep subsurface oceans liquid even at distances where solar heating is negligible. The process operates like a cosmic heating system, powered not by nuclear reactions or stellar radiation, but by the patient gravitational massage of orbital mechanics, maintaining warm havens in some of the coldest regions of planetary systems. The cosmic web's filamentary structure channels matter flows across hundreds of millions of light years, creating highways along which galaxies migrate and evolve. Gas and dark matter flow along these cosmic superhighways, moving from less dense regions toward the nodes where galaxy clusters form. This large-scale circulation pattern operates like a cosmic weather system, transporting material across vast distances and timescales. The flows are incredibly slow by human standards, but represent significant mass transport when integrated over cosmic time, helping to fuel star formation in galaxies and gradually altering the distribution of matter throughout the universe. Planetary ring systems demonstrate some of the most delicate gravitational choreography in the solar system, with countless particles maintaining complex orbital relationships across thousands of years. The rings of Saturn, for example, contain billions of ice and rock fragments ranging in size from dust grains to small moons, all orbiting in patterns so intricate they resemble cosmic clockwork. Shepherd moons maintain sharp edges on some rings through gravitational interactions, while resonances with larger moons create gaps and waves that propagate through the ring material like ripples in a cosmic pond. These systems can maintain their structure for millions of years, constantly reshaping themselves through gentle gravitational influences while preserving their overall appearance across geological timescales. Stellar winds from red giant stars create vast, tenuous atmospheres that extend far beyond the original boundaries of the stellar surface. As these aging stars expand and cool, they begin to lose mass through gentle stellar breezes that carry away their outer layers at speeds measured in kilometers per second, rather than the thousands of kilometers per second associated with more violent stellar phenomena. These winds can continue for millions of years, slowly but steadily reducing the star's mass, while enriching the surrounding interstellar medium with elements forged in the stellar core. The process is so gradual that the star maintains its basic structure throughout most of this mass loss phase, creating expanding shells of warm gas that glow softly in infrared wavelengths as they drift away from their parent star. The rotation periods of neutron stars provide some of the most stable timekeeping mechanisms known in the universe, with some pulsars maintaining their spin rates to within 1 part in a billion. These collapsed stellar cores can rotate hundreds of times per second while remaining more punctual than atomic clocks, creating lighthouse beams of radiation that sweep across space with metronomic precision. The stability of these cosmic timepieces is so remarkable that astronomers use them to detect subtle changes in space-time itself, including the passage of gravitational waves from distant cosmic events. Even over periods of years or decades, most pulsars maintain their timing with such accuracy that any deviation can reveal fundamental properties of physics and the structure of space itself. Protoplanetary disks around young stars evolve through phases of accretion and dispersal that can last for millions of years, gradually transforming from chaotic clouds of gas and dust into organized planetary systems. In the early stages, material spirals inward toward the central star, while simultaneously beginning to clump together under its own gravity. The process is neither violent nor sudden, but unfolds with the patience of geological time, as countless small collisions and gravitational interactions slowly build larger and larger aggregations of matter. Magnetic fields threading through the disk help regulate the flow of material, while radiation pressure from the young star gradually clears away the remaining gas, leaving behind a system of newly formed worlds orbiting in the quiet. The aftermath of their turbulent birth, the cosmic microwave background, exhibits tiny temperature variations that represent the seeds from which all large-scale cosmic structure eventually grew. These fluctuations, detected at the level of microkelvin differences across the sky, mark regions that were slightly denser or less dense than average in the early universe. Over hundreds of millions of years, gravity slowly amplified these tiny variations, causing matter to flow from less dense regions toward denser ones in a process so gradual that it can only be observed by comparing the universe at different epochs. The cosmic web of filaments and voids we see today represents the mature form of structures that began as whisper-soft variations in the temperature of ancient light. Globular clusters orbit their host galaxies in highly elliptical paths that can take them hundreds of millions of years to complete, carrying their populations of ancient stars on vast journeys through galactic space. These spherical collections of hundreds of thousands of stars formed early in cosmic history and have remained gravitationally bound ever since, serving as time capsules that preserve information about the conditions that existed when galaxies were young. During their orbital journeys, globular clusters can pass through the disk of their host galaxy, experiencing tidal forces that slowly strip away their outermost stars, but their cores remain intact, held together by the cumulative gravity of their stellar populations. The galactic fountain describes the gentle circulation of gas between a galaxy's disk and its extended halo, creating a cosmic recycling system that operates over hundreds of millions of years. Energy from stellar explosions and stellar winds heats gas in the galactic disk, causing it to rise into the halo where it cools and eventually falls back down like cosmic rain. This circulation helps regulate star formation by removing gas from active star-forming regions, while eventually returning it enriched with heavy elements produced by previous generations of stars. The process creates a kind of galactic breathing, with the disk alternately exhaling hot gas into the halo and inhaling cooler material that has been processed through this cosmic atmospheric cycle. Magnetic reconnection events in space plasma occur when magnetic field lines suddenly rearrange themselves, releasing stored energy in processes that can continue for hours or days, rather than happening instantaneously. These events are common throughout the cosmos, from the solar corona to the magnetospheres of planets to the regions around black holes. But they typically unfold gradually as magnetic field configurations slowly become unstable and then reorganize into lower energy states. The energy release heats the surrounding plasma and can accelerate particles to high speeds, but the overall process resembles a gentle untangling of cosmic magnetic knots rather than a violent explosion. Circumstellar disks around evolved stars create some of the most beautiful and geometrically perfect structures in the cosmos, with material arranged in thin, flat planes that can extend for hundreds of astronomical units from their central stars. These disks form when aging stars begin to lose mass through stellar winds that are focused into equatorial regions by magnetic fields or rotation, creating pancake-shaped distributions of gas and dust. The material in these disks can persist for thousands of years, slowly spiraling inward or being blown away by radiation pressure, while maintaining remarkably uniform thickness and radial structure throughout their evolution. Kozai resonances in hierarchical triple star systems create long-term orbital cycles that can last for millions of years, causing the orbits of the inner binary pair to oscillate between circular and highly elliptical configurations. These gravitational interactions occur when a distant third star influences the orbital plane of a closer binary system, causing the inner orbit to precess and change its eccentricity in regular cycles. The process operates so slowly that many cycles are required to significantly alter the system's configuration. But over cosmic time, these resonances can drive dramatic changes in stellar systems, sometimes leading to stellar mergers or the ejection of one component from the system entirely. The local bubble is a cavity in the interstellar medium surrounding our solar system that extends for hundreds of light years in all directions, created by ancient supernova explosions that cleared out much of the gas and dust in our cosmic neighborhood. This low-density region provides our solar system with a relatively clear view of distant stars and galaxies, while also reducing the amount of interstellar material that the Sun encounters as it moves through the galaxy. The bubble's boundaries are marked by denser shells of gas and dust that glow faintly in various wavelengths, creating a kind of cosmic cavern within which our solar system has been traveling for millions of years. Solar cycles create regular variations in stellar magnetic activity that can persist for decades or centuries, driven by dynamo processes deep within stellar interiors that generate and reverse magnetic fields on predictable timescales. Our Sun exhibits an 11-year cycle of magnetic activity that affects everything from sunspot numbers to the intensity of the solar wind. But longer-term variations can span multiple decades or even centuries. These cycles represent some of the most regular and predictable phenomena in astronomy, driven by the complex interplay between stellar rotation, convection, and magnetic field generation that operates like a cosmic clockwork mechanism buried deep within stellar cores. Tidal streams from disrupted satellite galaxies create some of the most delicate and extended structures in the universe, with stars stripped from their parent systems forming gossamer trails that can stretch for hundreds of thousands of light-years across space. These stellar streams mark the orbital paths of small galaxies that have been torn apart by the gravitational influence of larger systems, leaving behind rivers of stars that slowly disperse over hundreds of millions of years. The streams maintain their coherence for cosmic ages, serving as archaeological records of ancient galactic interactions, while gradually fading as their constituent stars drift apart under the influence of galactic tides. Herbig-Haro objects represent some of the gentlest manifestations of stellar outflows, created when jets from young stars interact with the surrounding interstellar medium to produce glowing knots and filaments of excited gas. These objects evolve over timescales of thousands of years as the stellar jets plow through varying densities of surrounding material, creating bow shocks and trailing wakes that can extend for several light years from their source stars. The entire phenomenon resembles cosmic calligraphy, with young stars writing luminous messages across space using jets of high-speed gas as their pens and the interstellar medium as their canvas. Planetary migration in young solar systems occurs through gravitational interactions with protoplanetary disks that can cause worlds to spiral inward or outward from their initial formation locations over millions of years. This process explains why many exoplanetary systems contain giant planets orbiting very close to their stars, despite the fact that such worlds likely formed much farther out where ice and gas could accumulate. The migration happens gradually as planets exchange angular momentum with the disk material, causing them to change their orbital radii while the disk slowly dissipates, eventually leaving behind planetary systems that may look very different from their original configurations. Cosmic void expansion creates regions of space that grow increasingly empty as the universe evolves, with matter flowing out along filaments toward denser regions where galaxy clusters form. These voids, which can span hundreds of millions of light-years, represent some of the most pristine environments in the cosmos, containing very little matter and experiencing minimal gravitational influences from distant structures. As the universe continues to expand, these voids grow larger and emptier, creating vast regions of space that approach perfect vacuum conditions while serving as quiet laboratories where the effects of cosmic expansion can be studied in isolation from the complex gravitational interactions that dominate denser regions. The asymptotic giant branch phase of stellar evolution creates some of the most spectacular mass loss episodes in the cosmos, as stars pulsate with periods of hundreds of days while ejecting their outer layers in a series of gentle but persistent stellar winds. These evolved stars can lose significant fractions of their mass over periods of thousands of years, creating expanding shells of gas and dust that eventually become planetary nebulae. The mass loss occurs through thermal pulses that periodically heat the stellar envelope, causing it to expand and cool until radiation pressure overcomes gravitational attraction and carries material away into interstellar space. Gravitational lensing by dark matter creates subtle distortions in the images of distant galaxies that can only be detected through careful statistical analysis of thousands of background objects. This weak lensing effect provides one of the most direct ways to map the distribution of dark matter throughout the universe, revealing how this invisible component of cosmic matter clumps and flows on the largest scales. The distortions are so small that they can only be measured by averaging over large samples of galaxies. But they provide a unique window into the hidden architecture of the cosmos that governs the formation and evolution of all visible structures. The galactic habitable zone represents a region within spiral galaxies where conditions may be most favorable for the development of complex life. Located at intermediate distances from the galactic center, where stellar densities are moderate and the frequency of disruptive events is relatively low. This zone avoids the inner regions where supernova explosions, gamma-ray bursts, and gravitational interactions are more common, while also staying within the disk where heavier elements necessary for rocky planet formation are sufficiently abundant. The concept suggests that the development of life may depend not only on planetary conditions, but also on a planet's location within its host galaxy. Stellar streams in the galactic halo create a fossil record of past merger events, preserving information about the small galaxies that were accreted by the Milky Way over billions of years of cosmic evolution. These streams can be traced back to their progenitor objects through careful analysis of stellar positions, velocities, and chemical compositions, allowing astronomers to reconstruct the merger history of our galaxy. Each stream represents a chapter in the story of galactic assembly, written in the motions of stars that were once part of independent stellar systems, but now follow the gravitational influence of their new host galaxy. The intra-cluster medium in galaxy clusters creates a hot, tenuous atmosphere that extends throughout the cluster volume, containing more mass in the form of ionized gas than all the galaxies within the cluster combined. This gas, heated to temperatures of tens of millions of degrees by the gravitational potential of the cluster, glows brightly in X-ray wavelengths and provides a record of the cluster's formation and evolution. The medium is stirred by the motion of galaxies through it and shaped by outflows from active galactic nuclei, creating complex structures that evolve over hundreds of millions of years as the cluster continues to accrete matter from its surroundings. Circumgalactic media form extended atmospheres around individual galaxies, containing vast reservoirs of gas that serve as both fuel for future star formation and repositories for material ejected by stellar feedback processes. These gaseous halos can extend for hundreds of thousands of light-years from their host galaxies, bridging the gap between the dense interstellar medium within galaxies and the even more tenuous intergalactic medium that fills the space between galaxies. The gas in these regions cycles slowly between different phases, sometimes cooling and falling into the galaxy to fuel star formation, other times being heated and expelled by supernova explosions and stellar winds. Post-asymptotic giant branch stars represent a brief but important evolutionary phase during which stars transition from the mass-losing giant phase to their final white dwarf state, often creating some of the most geometrically complex and beautiful planetary nebulae in the process. During this transition, which lasts only a few thousand years, the central star heats up rapidly, while its previously ejected envelope begins to glow as the stellar radiation ionizes the expanding gas. The interaction between stellar winds from different evolutionary phases can create intricate structures with multiple shells, jets, and symmetrical patterns that reveal the hidden complexities of stellar mass loss. Galactic chemical gradients reflect the inside-out formation history of spiral galaxies, with higher metallicities near galactic centers, where star formation began earliest, and lower abundances of heavy elements in the outer regions, where stellar populations are younger on average. These gradients develop over billions of years as successive generations of stars enrich the interstellar medium with heavier elements. But the enrichment process occurs more rapidly in the dense central regions, where star formation rates are higher. The gradients provide a fossil record of how galaxies assembled their stellar populations and how chemical elements have been distributed through galactic disks over cosmic time. Coronal mass ejections from stars create expanding bubbles of magnetized plasma that can persist for years as they propagate through interstellar space, carrying magnetic fields and energetic particles far from their stellar sources. These events represent some of the largest-scale magnetic phenomena in stellar systems, capable of affecting planetary atmospheres and space weather conditions across entire planetary systems. The ejected material travels at speeds of hundreds of kilometers per second, but can take months or years to traverse the distances between stellar systems, creating temporary enhancements in the interstellar magnetic field, strength, and particle density as they pass through different regions of space. The heliosphere creates a protective bubble around our solar system that extends far beyond the orbit of Pluto, formed by the solar wind pushing against the interstellar medium in a gentle but persistent cosmic standoff. This bubble, stretching over 100 astronomical units from the Sun, serves as a partial shield against high-energy cosmic rays from interstellar space, while allowing lower-energy particles to flow freely between stellar systems. The boundary region where solar and interstellar influences meet creates a complex transition zone that spacecraft like Voyager have crossed, revealing the delicate balance between our star's influence and the broader galactic environment that surrounds all planetary systems. Stellar multiplicity occurs in the majority of star systems throughout the galaxy, with binary and multiple star configurations representing the normal state of stellar existence rather than the exception. These gravitationally bound systems can persist for billions of years in stable orbital relationships, with companion stars following predictable paths around their common centers of mass. The orbital periods range from hours for the closest pairs to millions of years for the most widely separated systems, creating a hierarchy of cosmic partnerships that demonstrates gravity's ability to maintain long-term relationships across vast distances and timescales. Galactic rotation curves reveal the hidden presence of dark matter through the unexpectedly flat velocity profiles of spiral galaxies, where stars in the outer regions orbit at nearly the same speeds as those closer to the galactic center. This discovery, made through decades of careful observations, suggests that galaxies are embedded within much more massive and extended halos of invisible matter that provide the gravitational influence necessary to maintain these rotation patterns. The dark matter halos extend far beyond the visible boundaries of galaxies, creating invisible scaffolding that shapes galactic structure and evolution across cosmic time. Planetary atmospheric evolution unfolds over geological timescales as worlds gradually lose or gain atmospheric components through interactions with solar radiation, magnetic fields, and impacts from space debris. Rocky planets near their stars may lose their atmospheres to stellar winds and extreme ultraviolet radiation, while worlds farther out can maintain thick atmospheres for billions of years. The process involves complex feedback loops between atmospheric chemistry, planetary magnetic fields, and stellar evolution, creating diverse atmospheric outcomes that depend on the delicate balance between atmospheric retention and loss mechanisms. Superbubbles in the interstellar medium form when multiple supernova explosions occur within the same region over periods of several million years, creating cavities in space that can expand to diameters of thousands of light years. These cosmic soap bubbles are filled with hot, rarefied gas heated to millions of degrees by the combined energy of stellar explosions, while their walls consist of cooler, denser material swept up during the expansion process. The bubbles can break through the galactic disk and vent hot gas into the halo, creating chimneys that transport energy and enriched material far from the sites of stellar death and birth. Lagrange points in gravitational systems create regions of enhanced stability where small objects can remain in fixed positions relative to two larger masses, forming natural parking spots in space where cosmic debris and even spacecraft can maintain their locations with minimal energy expenditure. These gravitational sweet spots occur at 5 specific locations in any two-body system, with the most stable points forming equilateral triangles with the two primary masses. Asteroids and comets naturally accumulate at some of these locations, creating Trojan populations that share orbital paths with planets while maintaining fixed angular relationships that can persist for millions of years. Galactic bars are elongated structures of stars and gas that form in the central regions of many spiral galaxies, created by gravitational instabilities that cause stellar orbits to become aligned in preferred directions. These bars rotate as solid bodies, typically more slowly than the surrounding galactic disk, and play crucial roles in channeling gas toward galactic centers where it can fuel star formation or feed central black holes. The formation and evolution of galactic bars occurs over hundreds of millions of years as gravitational torques gradually reshape the distribution of matter within galactic disks, creating some of the most prominent and long-lasting features visible in spiral galaxies. Cosmic ray propagation through the galaxy follows complex paths determined by interactions with magnetic fields, causing these high-energy particles to take millions of years to travel distances that light covers in thousands of years. The particles bounce back and forth along magnetic field lines in a cosmic pinball game that can extend their journey times by factors of millions, allowing them to accumulate and mix throughout galactic volumes before finally escaping into intergalactic space. This diffusive propagation creates a relatively uniform background of cosmic rays throughout the galaxy, while also allowing these particles to sample conditions across vast regions of interstellar space. Magnetorotational instability drives accretion in many astrophysical systems, from protoplanetary disks around young stars to accretion disks around black holes. By converting magnetic energy into turbulent motion that allows material to spiral inward towards central objects. This process operates whenever ionized material with embedded magnetic fields rotates with a velocity that decreases outward, creating conditions where magnetic tension can destabilize circular orbits and drive accretion flows. The instability develops over timescales much shorter than the overall evolution of the accretion disk, creating a self-regulating mechanism that maintains steady inflow rates over millions of years. Stellar kinematics in the galactic disk reveal the complex history of stellar formation and migration, with different stellar populations exhibiting distinct patterns of motion that reflect their ages and birthplaces. Older stars tend to have more random motions and can venture farther from the galactic plane, while younger stars remain more tightly confined to circular orbits within the thin disk. These kinematic signatures preserve information about past episodes of galactic evolution, including mergers with satellite galaxies and the effects of spiral density waves that have stirred stellar motions over billions of years. Circumbinary planets orbit around both stars in binary systems, following complex gravitational paths that require careful orbital choreography to maintain stability over astronomical timescales. These worlds must orbit far enough from the central binary to avoid being gravitationally disrupted by the changing tidal forces as the two stars revolve around each other, but close enough to receive sufficient energy for potentially habitable conditions. The discovery of such planets demonstrates that planetary systems can form and survive in gravitational environments much more complex than our own solar system, expanding the range of cosmic environments where worlds might exist. Galactic chemical evolution proceeds through multiple generations of stellar nucleosynthesis, with each cohort of stars contributing slightly different elemental abundances to the interstellar medium based on their masses and evolutionary timescales. Low-mass stars contribute mainly carbon and nitrogen through stellar winds during their giant phases, while high-mass stars produce oxygen, silicon, and iron that get distributed through supernova explosions. This gradual enrichment process has been operating for over 10 billion years. slowly increasing the complexity of chemistry available for planet formation and potentially biological processes. Atmospheric tides on planets and moons create subtle but persistent forces that can gradually synchronize rotational and orbital periods over geological timescales, leading to tidally locked configurations where one hemisphere permanently faces the central body. This process occurs through the dissipation of tidal energy within planetary interiors, causing rotational periods to slowly lengthen or shorten until they match orbital periods. The timescale for achieving tidal locking depends on planetary size, orbital distance, and internal structure, but can range from millions to billions of years for different types of worlds. Stellar nursery regions within molecular clouds create multiple generations of star formation as the energy from early stellar births triggers collapse in neighboring cloud cores, propagating star formation across entire cloud complexes over timescales of tens of millions of years. This sequential star formation creates stellar associations with age gradients, where the oldest stars may have already evolved off the main sequence, while the youngest are still forming from the same parent molecular cloud. The process demonstrates how star formation can be self-sustaining within giant molecular clouds, creating extended episodes of stellar birth that gradually consume the available gas reservoir. Cosmic web filaments serve as highways for intergalactic gas flows that fuel ongoing star formation in galaxies by providing streams of pristine material from the primordial universe. These filaments, which can extend for hundreds of millions of light-years, channel cold gas from cosmic voids toward galaxy clusters and individual galaxies, maintaining the supply of raw material necessary for continued stellar birth. The gas flows along these filaments at velocities of hundreds of kilometers per second. But the journey from void to galaxy can take hundreds of millions of years as material follows the gravitational gradients established by dark matter structure. Precessional cycles in planetary orbits create long-term climate variations as the orientation of planetary spin axes slowly changes relative to orbital planes over timescales of tens of thousands of years. These Milankovitch cycles affect the distribution of stellar energy received at different planetary latitudes and seasons, potentially driving cyclical changes in atmospheric circulation patterns and surface conditions. The gravitational influences of other planets in the system determine the specific periods and amplitudes of these precessional variations, creating unique climate rhythms for each world based on its particular orbital and rotational configuration. Stellar wind interactions in binary systems can create complex shock structures and collision zones, where material from two stars meets and mingles, forming extended regions of heated gas that can persist for thousands of years as the stars maintain their orbital relationship. These wind collision regions often exhibit distinctive spectral signatures and can accelerate particles to high energies through shockwave processes, creating localized sources of high-energy radiation within stellar systems. The structures evolve slowly as stellar wind properties change during stellar evolution, but can maintain their basic configuration for significant fractions of stellar lifetimes. Galactic minor mergers contribute to the ongoing growth and evolution of large galaxies through the accretion of smaller stellar systems that add both stars and dark matter to the host galaxy's total mass inventory. These events occur much more frequently than major mergers, but deposit smaller amounts of material with each interaction, creating a continuous drizzle of galactic growth that can persist throughout cosmic time. The accreted material often settles into extended halo regions around the host galaxy, contributing to the buildup of stellar populations with distinct chemical and kinematic signatures that preserve information about their extragalactic origins. Resonant asteroid families form when larger parent bodies are disrupted by collisions or thermal stresses, creating groups of fragments that maintain similar orbital characteristics for millions of years after their formation. These asteroid families can be identified through statistical analysis of orbital elements and spectroscopic properties that reveal their common origins, providing insights into both collision processes and the internal structure of their parent bodies. The families evolve slowly under gravitational perturbations from planets, but their basic clustering in orbital space can persist long enough to serve as archaeological records of ancient impact events. Circumnuclear star formation occurs in the central kiloparsec regions of galaxies, where gas densities are high enough to trigger stellar birth, despite the disruptive influences of central black holes and their associated phenomena. These regions often exhibit enhanced star formation rates compared to galactic disks, creating populations of young, massive stars that can significantly affect the evolution of galactic centers through their stellar winds and eventual supernova explosions. The star formation process in these environments must overcome additional challenges posed by strong tidal forces, magnetic fields, and radiation from active galactic nuclei. Planetary ring shepherding demonstrates some of the most precise gravitational control mechanisms in planetary systems, where small moons maintain sharp boundaries in ring systems through resonant interactions that prevent ring particles from spreading into forbidden orbital zones. These shepherd moons can create gaps, maintain ring edges, and even generate spiral density waves that propagate through ring material, like ripples in a cosmic pond. The shepherding process operates through exchanges of orbital energy and angular momentum between moons and ring particles, creating a delicate balance that can persist for millions of years while continuously reshaping ring structure through gravitational choreography. Fossil groups represent the end state of galaxy cluster evolution, where a single dominant galaxy has consumed most of its companions through mergers and tidal disruption, leaving behind an extended X-ray halo that preserves evidence of the cluster's more populous past. These systems demonstrate that gravitational evolution in dense cosmic environments tends towards simplification over very long timescales, as the most massive objects gradually incorporate smaller neighbors through processes that can span billions of years. The remaining central galaxy often exhibits properties intermediate between normal elliptical galaxies and brightest cluster galaxies, reflecting its history of multiple mergers and accretion events. Stellar metallicity gradients in galactic disks preserve information about the inside-out formation of spiral galaxies, with higher abundances of heavy elements near galactic centers reflecting earlier and more intense episodes of star formation in these regions. The gradients develop over billions of years as stellar nucleosynthesis products are mixed through galactic disks by various transport processes, including stellar migration, gas flows, and turbulent mixing driven by supernova explosions and stellar feedback. These chemical patterns provide constraints on models of galactic chemical evolution and help astronomers understand how the building blocks of rocky planets and complex chemistry have been distributed throughout galactic systems. Magnetospheric substorms in planetary systems create dynamic auroral displays and energetic particle precipitation events that can persist for hours or days as magnetic field configurations adjust to changing stellar wind conditions. These phenomena occur when energy stored in planetary magnetic fields through interactions with stellar winds is suddenly released through magnetic reconnection processes, accelerating particles that subsequently interact with planetary atmospheres to create luminous auroral emissions. The substorm cycle represents a fundamental mode of energy transfer between stellar winds and planetary magnetospheres that operates throughout planetary systems wherever worlds possess significant magnetic fields. Binary evolution pathways lead to diverse outcomes depending on the initial masses and separations of stellar companions, ranging from detached systems that evolve independently to contact binaries where mass transfer fundamentally alters stellar evolution timescales and final fates. Common envelope evolution can bring stellar cores into close proximity, creating systems that may eventually merge or become sources of gravitational waves, while wider systems may experience only occasional episodes of mass transfer during giant phases. These evolutionary channels create the diverse population of compact object binaries observed throughout the galaxy, including the neutron star and black hole systems that produce gravitational wave signals detectable on Earth. Cosmic microwave background polarization patterns preserve information about the gravitational wave background produced during cosmic inflation, potentially providing observational access to energy scales and physical processes that occurred during the earliest moments of cosmic history. The polarization signal is extremely faint and requires sophisticated analysis techniques to separate it from foreground emission from our own galaxy and other sources. But successful detection could provide direct evidence for inflationary cosmology and constraints on the physics of the very early universe. The search for these primordial gravitational wave signatures represents one of the most technically challenging observational programs in modern astronomy. Planetary system architectures exhibit a wide diversity of configurations that reflect the complex interplay between planetary formation processes, migration mechanisms, and dynamical evolution over billions of years of system evolution. Hot Jupiters orbiting very close to their stars likely migrated inward from more distant formation locations, while compact systems of small planets may represent the outcomes of in situ formation within protoplanetary disks. The observed diversity suggests that planetary system formation is a highly stochastic process with outcomes sensitive to initial conditions and the detailed evolutionary history of each system, creating a vast range of possible planetary environments throughout the galaxy. Galactic fountain flows create a circulation pattern that transports gas between galactic disks and their extended halos. Driven by energy input from stellar feedback processes, that can lift material to heights of several kiloparsecs above galactic planes. The elevated gas eventually cools and falls back toward the disk under the influence of galactic gravity. But the circulation timescales are long enough that the gas can become chemically enriched through mixing with halo material during its journey. This fountain mechanism may play important roles in regulating star formation rates and maintaining the chemical evolution of galactic disks over cosmic time. Hierarchical structure formation in the universe proceeds through the gradual assembly of increasingly massive systems as smaller halos merge and accrete material from their surroundings, following predictable patterns determined by the properties of dark matter and the expansion history of the universe. Galaxy clusters represent the most massive bound structures in the present-day universe, but they continue to grow through ongoing accretion of galaxies and dark matter from surrounding regions. The hierarchical assembly process creates a cosmic web of structure that connects the smallest dark matter halos to the largest superclusters through a network of gravitational relationships that have been developing for over 13 billion years. Stellar nurseries operate on timescales so vast that entire civilizations could rise and fall during a single phase of star formation. Yet these cosmic maternity wards maintain their gentle, unhurried pace throughout the process. Within these vast molecular clouds, gravity works with infinite patience, slowly drawing together wisps of gas and dust across regions spanning hundreds of light years. The temperature in these nurseries hovers just a few degrees above absolute zero, creating conditions so serene that even the most delicate chemical bonds can form and persist for millions of years. As material gradually condenses under its own weight, it follows graceful spiral patterns dictated by magnetic fields and rotation, creating structures of such mathematical beauty that they seem almost choreographed by invisible cosmic composers. The process of accretion within these stellar wombs unfolds like the slowest possible dance, with particles joining together one by one in a ballet that can continue for tens of millions of years before the first nuclear fires ignite. Even when a protostar finally begins to shine, it does so gently at first, gradually warming its surroundings as it settles into the steady rhythm that will define its existence for billions of years to come. The leftover material from star formation doesn't disappear, but instead forms rotating disks that may eventually give birth to planetary systems, extending the creative process for millions of additional years as worlds slowly coalesce from cosmic dust and debris. Galactic streams of ancient starlight trace the orbital paths of disrupted stellar systems, creating some of the most delicate and extended structures visible in the night sky when observed with sufficiently sensitive instruments. These stellar rivers flow through space like cosmic calligraphy, written by gravitational forces acting over hundreds of millions of years, as smaller galaxies are gradually torn apart by the tidal influences of larger systems. The individual stars within these streams follow nearly identical paths through space, maintaining their coherent motion across vast distances while slowly spreading out like cosmic contrails that mark the passage of long-lost stellar communities. Each stream tells a story of cosmic archaeology, preserving information about galactic mergers and interactions that occurred billions of years ago when the universe was younger and galaxy formation was more active. The stars within these streams carry chemical signatures that reveal their common origins, allowing astronomers to trace their ancestry back to specific progenitor galaxies that no longer exist as independent systems. Some streams wrap completely around their host galaxies, creating gossamer halos of ancient light that testify to the gentle but inexorable power of gravitational disruption acting across cosmic time. The interplay between stellar winds and interstellar magnetic fields creates vast regions of sculptured space where matter flows along invisible highways, determined by the geometry of electromagnetic forces. These cosmic wind patterns can extend for thousands of light years, channeling material ejected by dying stars into graceful arcs and filaments that glow softly in wavelengths beyond human vision. The magnetic field lines threading through these regions act like cosmic yarn, weaving together disparate streams of stellar material into coherent structures that can persist for millions of years as they drift through interstellar space. Within these magnetized regions, charged particles spiral along field lines in helical paths that create natural particle accelerators stretching across interstellar distances. The acceleration process is gentle but persistent, gradually boosting particle energies over timescales measured in thousands of years as they bounce back and forth between magnetic mirrors formed by field line convergences. This cosmic particle processing creates populations of high-energy particles that eventually escape into the broader galactic environment, carrying with them the electromagnetic signature of their extended journey through structured magnetic landscapes. Planetary atmospheric circulation patterns develop through complex interactions between stellar heating, planetary rotation, and atmospheric composition, creating stable weather systems that can persist for centuries or millennia with only gradual changes in their overall characteristics. These atmospheric engines operate like planetary-scale heat pumps, redistributing energy from regions of net heating to areas of net cooling through circulation cells that can span entire hemispheres. The resulting wind patterns follow predictable mathematical relationships, determined by the balance between pressure gradients and rotational forces, creating jet streams and trade wind systems that maintain their basic structure across geological timescales. Even the most dynamic atmospheric phenomena, such as giant storm systems on gas giant planets, represent relatively stable features when viewed from cosmic perspectives, persisting for decades or centuries while maintaining their essential characteristics. These long-lived weather patterns demonstrate how fluid systems can achieve quasi-equilibrium states that balance energy input and dissipation across vast spatial and temporal scales, creating atmospheric landmarks that serve as reference points for understanding planetary circulation dynamics. The cosmic distance scale extends measurements from nearby stars to the edge of the observable universe through a carefully calibrated sequence of overlapping techniques, each building upon the precision achieved by previous methods in an elegant hierarchy of cosmic surveying. This astronomical measuring chain begins with geometric parallax measurements to nearby stars, extends through the brightness relationships of variable stars to intermediate distances, and reaches its greatest extent through observations of distant supernovae and the cosmic microwave background radiation. Each link in this cosmic chain has been painstakingly calibrated through decades of observation, creating a unified distance framework that allows astronomers to map the three-dimensional structure of the universe with remarkable precision. The reliability of this cosmic distance ladder depends on the careful overlapping of different measurement techniques, with each method providing independent confirmation of distances determined by other approaches within their respective ranges of applicability. This redundancy helps ensure that systematic errors in any single technique don't propagate throughout the entire distance scale, while also providing opportunities to refine and improve the calibration through comparison of results obtained using different methodologies. Tidal interactions between celestial bodies create some of the most precisely predictable phenomena in astronomy, with orbital mechanics calculations capable of forecasting the positions and orientations of moons, planets, and binary stars thousands of years into the future. These gravitational relationships operate with clockwork precision, following mathematical laws that remain constant across cosmic time, and allow astronomers to reconstruct past configurations of astronomical systems with the same accuracy they can predict future ones. The tidal forces responsible for these interactions work slowly but inexorably, gradually reshaping orbits and rotational states through energy dissipation processes that unfold over millions of years. Binary star systems provide natural laboratories for studying these tidal effects, as the gravitational interaction between stellar companions can synchronize their rotational periods with their orbital motions, creating tidally locked configurations where the same stellar hemispheres always face each other. This synchronization process represents a fundamental tendency toward minimum energy states in gravitational systems, with tidal friction serving as the mechanism that drives systems toward these stable equilibrium configurations over astronomical timescales. Cosmic ray interactions with interstellar matter create cascades of secondary particles that carry information about both the original high-energy events that produced them and the material they encountered during their journeys through galactic space. These particle showers develop as primary cosmic rays collide with atoms in interstellar clouds, producing sprays of lower-energy particles that continue to interact with surrounding matter in a branching pattern of nuclear reactions. The resulting particle populations create a kind of cosmic archaeology record, preserving signatures of supernova explosions, stellar wind acceleration, and magnetic field configurations that existed along their propagation paths. The cosmic ray population represents a dynamic equilibrium between sources that continuously accelerate new particles and loss processes that remove them from the galactic environment through escape or energy degradation. This balance creates a relatively stable background of energetic particles throughout galactic volumes, with local variations that reflect the distribution of sources and the large-scale magnetic field structure that guides particle transport. The cosmic ray pressure contributes to the support of interstellar gas against gravitational collapse, playing a subtle but important role in regulating star formation rates across galactic disks. Protoplanetary disk evolution unfolds through distinct phases, characterized by different physical processes, dominating the redistribution of matter and angular momentum within these rotating systems surrounding young stars. During the early phases, gravitational instabilities and magnetic turbulence drive rapid accretion of material onto the central star, while simultaneously beginning the process of grain growth that will eventually lead to planet formation. As the disk evolves, photoevaporation by stellar radiation gradually disperses the remaining gas, leaving behind a debris disk populated by larger solid bodies that continue to interact through gravitational and collisional processes. The transition between these evolutionary phases occurs over timescales of several million years, with the exact timing depending on stellar mass, initial disk properties, and environmental factors such as the presence of nearby massive stars that can influence disk evolution through external photoevaporation. The end result of this evolutionary sequence is typically a planetary system whose architecture reflects the complex interplay between formation processes, migration mechanisms, and long-term dynamical evolution that has operated throughout the system's history. Stellar population synthesis models allow astronomers to predict the integrated properties of stellar systems by combining theoretical understanding of stellar evolution with observed stellar mass distributions and star formation histories. These models treat stellar populations as composite systems whose overall characteristics result from the combined contributions of stars with different masses and ages, each contributing according to its individual evolutionary state and intrinsic properties. The modeling process requires careful consideration of stellar initial mass functions, binary star evolution, and chemical evolution effects that can significantly influence the predicted colors, luminosities, and spectral features of stellar populations. The success of these population synthesis approaches in reproducing observed properties of star clusters, galaxies, and other stellar systems demonstrates the fundamental consistency of stellar evolution theory, with astronomical observations across a wide range of cosmic environments. The models also provide powerful tools for interpreting observations of distant galaxies, allowing astronomers to infer star formation histories and chemical evolution patterns from photometric and spectroscopic data obtained with modern telescopes. Magnetohydrodynamic processes in astrophysical plasmas create complex interactions between magnetic fields and fluid motions that can generate turbulence, drive accretion flows, and launch powerful outflows from various types of cosmic systems. These magnetofluid phenomena operate through the coupling between electromagnetic forces and pressure gradients in ionized gases, creating feedback mechanisms that can either enhance or suppress various astrophysical processes, depending on the specific magnetic field configurations and plasma conditions involved. The mathematical description of these interactions requires sophisticated numerical simulations that can capture the nonlinear evolution of magnetic field structures as they respond to changing plasma conditions. The universality of magnetohydrodynamic physics means that similar processes operate across an enormous range of cosmic environments, from the interiors of stars to the accretion disks around black holes, with only the relevant length scales, time scales, and magnetic field strengths varying between different applications. This commonality allows insights gained from studying one type of magnetohydrodynamic system to inform understanding of others, creating a unified framework for understanding magnetic phenomena throughout the universe. Circumstellar envelope evolution around evolved stars creates some of the most geometrically complex and visually striking structures in the cosmos. As stellar winds interact with material ejected during earlier evolutionary phases to produce intricate patterns of shells, jets, and asymmetric outflows, these envelopes develop over timescales of thousands to tens of thousands of years as central stars transition through their final evolutionary stages, with changing stellar wind properties and binary interactions often contributing to the creation of highly structured morphologies. The resulting nebular structures serve as laboratories for studying stellar mass loss processes, binary evolution, and the chemical enrichment of interstellar space through stellar nucleosynthesis products. The diversity of planetary nebula morphologies reflects the complex interplay between stellar evolution, binary interactions, and magnetic field effects that can channel and focus stellar winds into collimated outflows or create multipolar structures with remarkable symmetries. The evolution of these systems continues long after the central star has settled into its white dwarf configuration, as the expanding nebular shells gradually disperse into the surrounding interstellar medium, while the ionizing radiation from the central star slowly fades. Cosmic web connectivity determines how matter and energy flow between different regions of the universe, with filamentary structures serving as conduits for gas transport from low-density voids toward high-density nodes where galaxy clusters form. This large-scale architecture creates a hierarchical pattern of matter distribution that influences galaxy formation and evolution through the regulation of gas accretion rates and the frequency of galaxy interactions. The filaments themselves are not static structures, but evolve continuously as cosmic expansion stretches their lengths, while gravitational attraction increases their internal densities, creating a dynamic network that connects all massive structures in the universe. The intersections of multiple filaments create special environments where galaxy formation can proceed more rapidly than in typical cosmic locations, leading to the formation of rich galaxy clusters and superclusters that represent the most massive gravitationally bound systems in the present-day universe. These cosmic intersections also serve as focal points for intergalactic gas flows that can fuel continued star formation in galaxies long after they might otherwise have exhausted their internal gas supplies. Resonant coupling between different oscillation modes in stellar interiors creates complex pulsation patterns that can provide detailed information about stellar structure and evolutionary state through the techniques of asteroseismology. These stellar seismic studies reveal the internal rotation profiles, convection zone boundaries, and chemical composition gradients that would otherwise remain hidden beneath stellar surfaces, allowing astronomers to test theoretical models of stellar physics with unprecedented precision. The pulsation frequencies observed in variable stars depend sensitively on stellar mass, age, and internal structure, making them powerful diagnostic tools for understanding stellar evolution processes. The mathematical analysis of stellar oscillations requires sophisticated computational techniques that can model the propagation of acoustic and gravity waves through stratified stellar interiors with varying temperature, density, and composition profiles. The resulting frequency spectra contain rich information about stellar properties that can be extracted through comparison with theoretical predictions, creating opportunities for precision stellar astrophysics that complement traditional observational approaches based on surface properties alone. Galactic archaeology uses the chemical compositions and kinematic properties of individual stars to reconstruct the formation history of the Milky Way and other galaxies. Treating stellar populations as fossil records that preserve information about past episodes of star formation, chemical enrichment, and dynamical evolution. This approach relies on the fact that stars preserve throughout their lifetimes the chemical signatures of the interstellar medium from which they formed, allowing their abundance patterns to serve as chemical clocks that can be used to date different phases of galactic evolution. The kinematic information provided by stellar proper motions and radial velocities reveals how stellar orbits have been modified by past merger events, spiral density waves, and other dynamo-ical processes. The combination of chemical and kinematic data from large stellar surveys has revolutionized understanding of galactic evolution by revealing the complex layered structure of galactic components and the detailed history of accretion events that have shaped the present-day Milky Way. These studies demonstrate that galaxy formation has been an ongoing process throughout cosmic history, with major structural components continuing to evolve through minor mergers and internal dynamical processes even in the present epoch. Exoplanet atmospheric characterization through transit spectroscopy and direct imaging provides increasingly detailed information about the chemical compositions, temperature structures, and circulation patterns of worlds orbiting other stars, revealing the diversity of atmospheric conditions that exist throughout the galaxy. These observations demonstrate that planetary atmospheres can exhibit a wide range of chemical compositions and physical properties, from hydrogen-dominated gas giants to rocky worlds with tenuous or substantial secondary atmospheres created through volcanic outgassing or atmospheric retention processes. The study of exoplanet atmospheres also provides insights into atmospheric evolution mechanisms and the potential habitability of different types of worlds. The atmospheric properties of exoplanets depend on complex interactions between stellar irradiation, planetary mass and composition, magnetic field strength, and atmospheric escape processes that operate over geological timescales too. These studies are revealing that atmospheric shape, the long-term evolution of planetary environments, retention and loss, represent fundamental processes that determine which worlds can maintain conditions suitable for liquid water and potentially biological processes over the timescales required for life to develop and evolve. Gravitational wave astronomy has opened a completely new observational window on the universe, allowing direct detection of space-time distortions produced by the most energetic events in cosmic history, including black hole mergers, neutron-star collisions, and potentially even signatures from the inflationary epoch immediately following the Big Bang. These observations provide unique information about extreme gravitational environments that cannot be studied through electromagnetic radiation, revealing the properties of compact objects and testing fundamental predictions of general relativity under conditions that cannot be reproduced in terrestrial laboratories. The gravitational wave signals carry information about the masses, spins, and orbital parameters of merging compact objects, as well as providing constraints on the equation of state of nuclear matter and the expansion history of the universe. The network of gravitational wave detectors currently operating around the world represents a new kind of cosmic observatory that can localize sources in three-dimensional space and trigger coordinated observations with traditional telescopes to study the electromagnetic counterparts of gravitational wave events. This multi-messenger approach to astronomy promises to revolutionize understanding of neutron star mergers, gamma-ray bursts, and other high-energy phenomena by providing complementary information about the same astrophysical events through multiple observational channels. Solar system dynamics continue to evolve through subtle gravitational interactions between planetary bodies, with long-term orbital changes occurring through resonant coupling mechanisms and tidal dissipation processes that operate over millions to billions of years. These evolutionary processes include the gradual outward migration of the Moon due to tidal friction, the slow changes in planetary orbital eccentricities and inclinations caused by mutual gravitational perturbations, and the ongoing capture and ejection of small bodies from the outer solar system through gravitational interactions with the giant planets. The current configuration of the solar system represents a temporary state in its ongoing dynamical evolution, with future changes predictable through numerical integration of the equations of motion over extended time periods. The stability of the solar system over geological timescales has been a subject of intensive study using both analytical techniques and numerical simulations, revealing that while the system exhibits overall long-term stability, individual orbital elements can undergo significant variations over million-year timescales. These dynamical studies also provide insights into the early history of the solar system and the processes that led to the current planetary configuration through migration and dynamical evolution during the epoch of planet formation. Stellar magnetic field generation through dynamo processes creates the complex magnetic structures observed on stellar surfaces and in stellar coronae, with field strengths and geometries that depend on stellar rotation rates, convection zone properties, and evolutionary states. These magnetic fields play crucial roles in driving stellar winds, heating stellar atmospheres, and modulating stellar activity cycles that can persist for decades or centuries with varying degrees of regularity. The solar magnetic field represents the most thoroughly studied example of stellar magnetism, with observations revealing the detailed structure of magnetic flux tubes, coronal loops, and the large-scale field reversals that occur during the 11-year solar activity cycle. Stellar magnetic fields also influence planet formation and evolution through their effects on protoplanetary disk structure and evolution, with magnetic coupling between stars and disks playing important roles in regulating accretion rates and angular momentum transport during the early phases of planetary system development. The interaction between stellar magnetic fields and planetary magnetospheres creates complex electromagnetic environments that can affect atmospheric retention and the potential habitability of close-in planets around active stars. Interstellar chemistry laboratories exist within the cold molecular clouds that drift between stars, where complex organic molecules form through processes so gentle they would be impossible to replicate under terrestrial conditions. In these cosmic chemistry sets, temperatures drop to within a few degrees of absolute zero, creating environments where atoms move so slowly that even the most delicate chemical reactions can proceed without disruption. Dust grains serve as catalytic surfaces where hydrogen atoms can find each other and combine into molecules, while ultraviolet radiation from distant stars provides just enough energy to drive more complex chemical pathways without destroying the fragile products. These interstellar laboratories have been operating for millions of years, slowly building up inventories of organic compounds that include alcohols, aldehydes, and even amino acid precursors. The chemistry unfolds with infinite patience, as molecules spend thousands of years drifting through space before encountering the right conditions for their next chemical transformation. Some of these molecules eventually become incorporated into new stellar systems during star formation, seeding planetary environments with the raw materials that could eventually give rise to biological processes. Planetary magnetic field interactions with stellar winds create vast invisible sculptures in space, forming magnetospheric structures that can extend millions of kilometers from planetary surfaces while remaining completely transparent to visible light. These magnetic bubbles serve as shields that deflect charged particles from stellar winds, creating bow shock regions where the stellar wind encounters resistance and flowing around planets like cosmic rivers diverted by magnetic obstacles. The resulting magnetospheric configurations can persist for billions of years, slowly evolving as stellar activity levels change and planetary magnetic fields strengthen or weaken over geological time. Within these magnetospheric cavities, trapped particle populations undergo complex motions guided by magnetic field lines, creating natural particle accelerators that operate continuously throughout planetary system lifetimes. The particles follow helical paths around magnetic field lines, while simultaneously bouncing back and forth between magnetic mirror points, creating a kind of cosmic pinball machine where individual particles can remain trapped for years or decades before finally escaping into interplanetary space. The evolution of stellar clusters follows predictable patterns as gravitational interactions gradually disperse their member stars across galactic volumes, creating expanding associations that eventually blend into the general stellar population of their host galaxies. This cluster dissolution process operates through a series of gentle gravitational encounters between cluster members, with each interaction slightly altering stellar velocities until some stars acquire enough energy to escape the cluster's gravitational potential. The process can take hundreds of millions of years to complete, during which time the cluster gradually loses its most energetic members while its remaining stars continue to orbit within an increasingly diffuse gravitational system. The final stages of cluster evolution often leave behind small groups of gravitationally bound stars that represent the dense cores of the original associations. while the majority of cluster members become part of expanding stellar streams that trace out the cluster's orbital path through galactic space. These fossil stellar groups preserve chemical and kinematic signatures of their common origin for billions of years after their parent clusters have completely dissolved. Atmospheric escape processes on rocky planets operate through a variety of mechanisms that can gradually strip away planetary atmospheres over geological timescales, with the efficiency of these processes depending on planetary mass, atmospheric composition, stellar activity levels, and magnetic field strength. Thermal escape occurs when atmospheric molecules acquire enough kinetic energy from solar heating to exceed the planetary escape velocity, while non-thermal processes can accelerate specific atmospheric components through interactions with stellar wind particles or ultraviolet radiation. These escape mechanisms work slowly but persistently, potentially transforming planetary environments over billions of years of evolution. The balance between atmospheric loss and replenishment through volcanic outgassing, comet impacts, and other sources determines the long-term evolution of planetary atmospheres and their potential to maintain conditions suitable for liquid water and biological activity. Planets with strong magnetic fields can retain their atmospheres more effectively by deflecting charged particles that would otherwise erode atmospheric components through sputtering and ionospheric heating processes. Cosmic dust grain formation occurs in the atmospheres of evolved stars and the ejecta of stellar explosions, where condensation processes create tiny solid particles that serve as the building blocks for future generations of stars and planets. These microscopic grains begin their existence in the hot, dense environments around dying stars, where heavy elements produced by stellar nucleosynthesis condense into refractory compounds that can survive in the harsh conditions of interstellar space. Once ejected from their stellar sources, these dust grains embark on million-year journeys through galactic volumes, gradually accumulating mantles of frozen gases and organic compounds as they drift through molecular clouds. The dust grains play crucial roles in interstellar chemistry by providing surfaces where gas phase atoms can stick together and form more complex molecules, while also absorbing and scattering starlight in ways that affect the thermal balance and chemical conditions within molecular clouds. This cosmic recycling of stellar material creates the raw ingredients for planetary system formation, with dust grains eventually becoming incorporated into protoplanetary disks, where they serve as the seeds for planet formation through accretion processes. Binary star evolution pathways create some of the most complex stellar evolution scenarios in the universe, as gravitational interactions between stellar companions can fundamentally alter the evolutionary trajectories of both stars compared to their single-star counterparts. Mass transfer episodes between binary components can rejuvenate aging stars by providing them with fresh hydrogen fuel, while also creating exotic stellar configurations, such as blue stragglers that appear younger than their chronological ages would suggest. The timing and extent of mass transfer depend on the initial orbital separation and stellar masses, creating a wide variety of possible evolutionary outcomes. Common envelope evolution represents one of the most dramatic phases of binary star evolution, occurring when one stellar component expands to engulf its companion during the giant phase. The resulting frictional interactions can cause the stellar cores to spiral inward through the common envelope material, potentially leading to very close binary systems or even stellar mergers. These processes operate over timescales of thousands of years, extremely rapid by astronomical standards. Yet they can determine the ultimate fate of binary systems and influence their potential to produce various types of compact object pairs. Galactic chemical enrichment proceeds through the gradual accumulation of heavy elements produced by successive generations of stars, with different stellar mass ranges, contributing distinct suites of elements to the interstellar medium through stellar winds and explosive events. Low-mass stars contribute carbon and nitrogen through mass loss during their giant phases, while intermediate mass stars add oxygen and neon, and the most massive stars produce silicon, iron, and other heavy elements that get distributed through supernova explosions. This ongoing enrichment process has been operating for over 10 billion years, slowly increasing the metallicity of galactic gas and enabling the formation of increasingly complex chemistry in subsequent generations of stars and planets. The spatial distribution of heavy elements within galaxies reflects the complex interplay between stellar nucleosynthesis, mixing processes, and gas flows that transport enriched material between different galactic regions. Radial metallicity gradients in spiral galaxies preserve information about their formation histories and the efficiency of various mixing mechanisms, while vertical gradients perpendicular to galactic disks reveal how supernova explosions and stellar winds have transported heavy elements into galactic halos over cosmic time. And now, as we reach the end of our gentle journey through the cosmos, let your thoughts settle like stardust, finding its place among the stars. We've drifted together through the patient rhythms of the universe, from the quiet breathing of galaxies to the soft whisper of ancient light that still bathes everything in tender warmth. In all these cosmic truths, there's a beautiful reminder that even in the vastest scales of space and time, peace exists, patience endures, and gentle processes shape the magnificent tapestry of existence. Sleep well, knowing you're part of this serene cosmic dance, and thank you for sharing this tranquil exploration with me tonight.